Yesterday we started looking at constructing an electrochemical cell to create a battery. When you are creating an electrochemical cell, you need to start by determining which of the chemical reactions is going to be reduced and which of the chemical reactions is going to be oxidized. In order to do that, you need to use a table of standard reduction potentials, which you will find in your yellow data booklet. So if you can please take those out and turn to the page with the reduction potentials, which is page 10. Okay, page 10. In this particular system, we have silver ions and silver atoms, lead ions and lead atoms. The reduction potential ranks chemical reactions, specifically reduction reactions, in terms of their ability to gain electrons. Substances that are the highest on that table are going to be the reduction reactions in the electrochemical cell. If you take a look at that yellow table, what do you notice is the top substance? Take a look at your table. What is the top substance?
Silver.
Okay.
Oh, wait.
We're not comparing silver versus lead. I want you to look at the top table and find the strongest reduction reaction.
Fluorine.
Fluorine. Why?
Because it has the highest electronegativity.
Exactly. It has the strongest pull of electrons of any atom on the periodic table.
So does that mean that, say, like, if we're going to compare silver and lead, we could just read the electronegativity?
Okay, let's test it out.
Silver has 1.9 and lead has 1.8.
Okay.
So silver's stronger.
Let's go to page 10. The two reduction reactions you need to look up are Ag positive plus 1 electron to Ag, and Pb2 positive plus 2 electrons is going to give you solid lead. Which of those two reduction reactions is higher on page 10?
Silver.
Okay. Does that match your prediction? It does. Let's try another one. Give me two metals on the periodic table, please.
Titanium and nobile.
Okay, let's double check and make sure that they appear on the right-hand side of your table. Because if they don't appear on the right-hand side of the table, there's no sense using them. Okay, go to page 10. Okay, so look on the right-hand side here. So we need two substances from this side.
Copper and cobalt.
Okay, so when you say copper and cobalt, let's just go here. Are you using the copper 1 ion or are you using the copper 2 ion? So the copper 2 ion is gaining 2 electrons to become solid copper. What about cobalt? You're using cobalt too?
Yeah, that's one.
Okay. CO2 positive plus 2E. Let's take a look at the periodic table. What is the electronegativity for copper?
1.9.
What is the electronegativity for cobalt?
1.9.
Oh, what's the problem?
So when electronegativity is the same, you'd have to go to look at this table.
I would suggest you always start by going to that table.
Okay.
Okay, just because it's going to be some that are extremely close.
Negative 0.28.
Negative 0.3 what?
28.
Negative 0.28 what?
Oh.
Okay, that's its potential. which means we actually have to, that releases that amount of energy when the reduction happens. If you take a look at this reaction with cobalt 2 positive gaining 2 electrons and copper 2 positive gaining 2 electrons, which of those two reactions is higher up?
Copper.
Pardon me?
Copper.
Copper. This is going to be the reduction reaction. This other one has to swap around. You have to flip that equation, and you have to make it CO to CO2 positive plus 2 electrons. And that is going to be the oxidation reaction. Something has to lose electrons in order for something to be able to gain electrons. You can't have two reduction half reactions going on in an electrochemical cell. Okay. That table will always help you figure out which one is going to be the reduction reaction and which one is going to be the oxidation reaction. If we continue on this equation, erase this here. Can you please draw what your electrochemical cells will look like? We're going to go with the 2-cup method of showing an electrochemical cell. You should have 2 cups. In 1 cup, you're going to show the reduction reaction. In the 2nd cup, you're going to show the oxidation reaction. The reduction reaction is copper 2 positive plus 2 electrons, which will give you solid copper. That means this electrode must be made out of copper. Is this going to be the anode, or is it going to be the cathode? Cathode, remember anox and red cat. Reduction always happens at the cathode. The copper electrode must be in a solution which contains copper 2 positive ions. How are we going to create a solution with copper 2 positive ions? Exactly. We're going to choose something that has a negative ion that dissolves really, really well. By choosing copper 2 nitrate, we choose a very highly soluble substance which will break apart or dissociate when it's dissolved into water and gives us copper 2 positive ions and nitrate ions. In the next beaker, we have a strip of cobalt. We must have cobalt 2 positive ions and nitrate ions. It is this area where the cobalt will actually lose electrons and be oxidized right here. This makes cobalt the anode. The electrons will travel from the site of oxidation to the site of reduction. We also must have a salt bridge which links these two so that the nitrate ions and in this case it will be the cobalt ions, can migrate across the salt bridge in order to create a neutral solution. Yes?
I got a question totally off of the marks. Those new elements that they added yesterday, could you start seeing them working their way into chemistry equations like this?
Unlikely. We would be able to use the 4 newly named elements here because they exist for such a short period of time. They're not practically useful. Right now, they're mainly used for scientific research. They break down within nanoseconds of being created. Perhaps in the next decade or so, we will find a way to stabilize those atoms, and then perhaps they could be used for a useful purpose within society. Right now, it's mainly a research endeavor. How are you feeling with this stuff so far? Do you feel like you could come up with an electrochemical cell if I gave you two half reactions? Do you need one more example? No, you're good. Okay, let's talk about cell notation then. Okay, I'm having problems with Microsoft Word right now, so we are on page 18 of the notes. We're going to look at representing cells using cell notation. Cell notation allows us to communicate what the electrode and its key ion in the solution is. This makes it easier for other people to understand what it is we're using. When you represent the copper half cell, for example, we would put the solution ion and the identity of what's making up the electrode. The solution ion comes first here. The copper electrode is made up of copper, so it is Cu. When we write out both the oxidation and the reduction notation, we always write the oxidation half cell first, and the solution and the electrode positions are reversed. The reduction half reaction notation is written second. If we go back to our original electrode cell, which consisted of zinc and copper, this part of the notation represents oxidation. In our zinc copper cell, what was undergoing oxidation? Zinc ions. Okay. Or sorry, zinc atoms. The electrode was zinc. The solution consisted of zinc 2 positive ions. On this side of the double line, we write our reduction half reaction. We have our solution of copper, which contained copper 2 positive ions, and our electrode was made up of copper. Why do you think we have to write the oxidation half cell first in this notation style? What's so important about oxidation?
It's the one that gives up the electrons.
Exactly. Something cannot take electrons unless something else gives up the electrons. The oxidation half cell always comes first to show that. We're going to now summarize electrochemical cells in the table below. We have the anode, cathode, electron flow, ion flow, and spontaneity. The anode is site of what? Anode is the site of oxidation. What happens during the process of oxidation?
Loss of electrons.
Okay, so it produces electrons from oxidation. If the anode is the source of electrons, what charge do you think it's going to have?
Negative because it's producing electrons.
Ah, exactly. The cathode is the site of what?
Reduction.
Reduction. Blank electrons to create reduction.
Loses.
It's gaining electrons. Do you think it's going to be positive or negative?
Negative because it's still gaining electrons.
But if you think of a battery, if you look at the edges of each side of the battery, one side is negative and the other side is positive.
So it's
So you have
neutral?
two. It's the positive end of a battery because you have the copper 2 positive ions which are going to take the electrons. So the cathode is positive in charge. Which direction are the electrons going to flow?
Left to right.
It's going to go from anode to cathode or cathode to anode.
Reduction.
Cathode to anode.
Has to go from anode to cathode. It has to go from the side of where the electrons are freed to the side where the substance is going to gain the electrons. Ion flow. Now we're talking about the salt bridge. Blank, negative ions migrate towards the anode. Do you remember the fancy word for a negative ion? No? Had to identify positive and negative ions way back in science 10. Anions are negative. A-N-I-O-N-S. Anions, or substance with a negative charge.
Cations.
There you go. You've got the other word. Cations are the positive ions, and they flow towards the cathode. Spontaneity. Blank, blank, voltage.
High power voltage.
Continual.
Okay. It's always positive voltage.
What's the other blank for? Oh,
Always positive voltage. By definition, an electrochemical cell is always a spontaneous chemical reaction. It always produces energy. An electrolytic cell requires a battery to be added to pump electrons in the opposite direction of natural electron flow. So please go back to page 19. We're going to fill out standard electrode potential section. As metals only have a few valence electrons compared to nonmetals, metals are most likely to blank electrons. Lose. This means that they are likely to be,
Cathodes.
yeah, that could be a possibility. But think about the redox process. If something loses electrons, we say it has been oxidized. This means that metals are more likely to be oxidized and are stronger something agents, reducing agents. Metals differ in how easily they part with the electrons. The blank blank arranges metals in order of how easily oxidized, or sorry,
Sulfurate.
how easily reduced they are.
Sulfurate.
Electropotential.
Standardized table. Standardized table. What we're going to do now is to figure out how much electricity is trapped in, or could be produced by an electrochemical cell. Please go to page 22. Page 22.
Is that your final answer?
What I want to do, or what I want you to do, is to create an electrochemical cell that is made up of aluminum, aluminum 3 positive, lead, and lead 2 positive.
That's me.
Let's write out 2 reduction reactions.
Never.
Please write out 2 reduction reactions. What's really nice is you can find the reduction reactions in your standardized table. You shouldn't have to guess what a reduction reaction looks like. If you're guessing, then that could be an issue because something's been chosen that is not in there. We have 2 possible reduction reactions. How are we going to figure out which one is actually going to be the reduction reaction in the electrochemical cell?
Whichever one's higher.
Exactly.
Where's Al3 positive?
Down towards the bottom.
Oh,
Keep going. Did you find it?
I found it.
Okay. So Al3 positive aluminum. Oh, sorry, that is aluminum. I wrote it down in the wrong place. If we go up to the lead, which one is higher?
The top one. Bottom one. The bottom one.
Okay, the bottom one is higher in your standardized table, which means that it is going to be the reduction reaction. That means we need to make this aluminum one an oxidation. How are we going to do that? Flip it. If I flip it, it becomes Al. Al3 positive plus 3 electrons. If I flip the equation, I must also do this. If I make something an oxidation equation, I must also change the sign of the voltage. Before we do anything else, Do you notice a problem with the number of electrons gained and lost here?
It's unequal.
It is. How would you resolve that?
Multiply.
Yes. What would you multiply the aluminum equation by?
2.
So 2, 2. This is going to become 6. Do not change this number back here. Okay? Do not change the voltage. Even if you multiply the rest of the equation, don't change the voltage. What are you going to have to multiply the reduction equation by? If I do that, I then have 3 parts Pb2 positive plus 6 electrons three parts lead. Now, if I take a look at this, I have 6 electrons which are lost by the aluminum, and I have 6 electrons which are gained by the aluminum. Please add these two half reactions together. Please add the two half reactions together. How could we predict the electrical potential of the circuit?
You add the two together.
1.66 volts plus negative 0.13 volts gives us
0.53.
1.5 volts is the voltage of one of these batteries.
Isn't that negative 1.66?
We flipped the equation
Oh, so then
from a reduction to an oxidation
Alright,
equation,
so I just
which means it is now a positive number.
and that's one of the batteries.
Okay. Yeah. This particular battery is, I believe, a cadmium battery. It doesn't label it. Please finish this diagram. In this diagram, you need to show your electrolytic solutions, your external circuit, your salt bridge. You need to label your anode and cathode and indicate which electrode is going to be negative and which electrode is going to be positive. Which one of the metal strips is going to be the anode? Okay, so the anode has to be the aluminum because the aluminum is the site of oxidation. Is the anode going to be positive or is it going to be negative? It's the negative terminal in the battery because it's the source of electrons. Lead is going to be the cathode, and it is going to have a positive charge. Which direction are the electrons going to go through the external wire? If I link these two strips here to here with a wire, Electrons always flow from anode to cathode. You need a salt bridge. The negative ions always flow to the anode. The positive ions always flow to the cathode. And that's an electrochemical cell.
What is an alkaline battery? Like, how does that work?
Okay, what does the word alkaline mean?
Addition. I'm just kidding, I don't know.
It means basic.
So it's using an acid, use the base.
Use the base, yes. Why do you think we would use a base instead of an acid?
It's more effective. It won't eat necessarily, like it won't eat what you put into it.
One of the characteristics of an acid is that it eats metal. Have you ever pulled off all the plastic?
Yeah.
Yeah?
I have a battery that I did that at home with, and I went to go try to use it or something the other day, and I went to squeeze it, and a whole bunch of that stuff came out.
Did it burn?
I never got it on my hand, but
Okay, good. Because you don't want that stuff all over your hand. Even though it's a base, bases are still corrosive. Underneath this plastic, this whole battery is metal. If this was an acidic dry cell battery, the acid would eventually eat away all the metal. Then it would start leaking all over whatever it was inside. Imagine this was the battery that powered your cell phone.
So if it doesn't have that around it, then it will leak.
No, this is a basic cell. The paste inside of here is basic. Bases do not eat metals. Every once in a while, it will leak paste. It happens. But it's not necessarily eating or leaking because of it eating away the side of the battery. Metals will be eaten by acids. Think about your car battery. What houses your car battery?
plastic.
Plastic. The reason why the outside surface of your car battery is plastic is because the electrolytic solution inside a car battery is sulfuric acid. You don't want that eating through the sides and starting to eat your car. Not good. It is possible for a battery to crack and leak inside of your car. One of the dangers with that is as that acid reacts with the metal, it produces hydrogen gas. What happens exactly?
My brother had one explode on him before.
Really?
A bad tractor battery, yeah. We had to move it and it just like blew up.
Yep. So there must have been a leak somewhere and a metal came into contact with that acid and it produced hydrogen gas.
Yeah.
It's extremely dangerous.
He got all the acid like all over him and it just like burned holes in like all his clothes.
I'm amazed there was even any clothes left once that acid got onto them. But, so you have to be very careful when you're replacing a battery. Wear protective clothing if you're going to work with your battery and replace it on your own, just in case.
Never.
Pardon me?
I said never.
Yeah. Okay. To finish up the class today, I am going to give you a question from scratch. I want you to have a piece of paper. Okay, I need to find, okay, where are you, Mercury? These batteries here are mercury cadmium batteries. Your job is to basically do practice problem 2, but with new information. You need to do all the parts of practice problem 2 with this combination. Give it a try.